as you know, unfortunately, Yossi couldn't make it due to the conflict in the Middle East. And we are very glad that Gustavo agreed to give the lecture almost the last minute. We asked him. And okay, we'll introduce a bit about Gustavo. So Gustavo did his undergraduate from University of Buenos Aires in Argentina. And then after that, he did his PhD in University of Massachusetts, Amherst, in the United States in 1993. After that, he did several postdoc in the States, Fermilab, University of Wisconsin, and Boston University. And he started as a scientist in Lawrence Berkeley National Laboratory in the States. And in 2004, he moved to Sao Paulo, and he has been a professor since in University of Sao Paulo since 2004 until now. And his work is basically on physics beyond the standard model. And especially, I think, to understand why the Higgs or weak scale is so small compared to some new physics scale, probably the grand unified scale. And okay, I will pass my stage to Gustavo.
Okay, thanks, Sheng, for the kind introduction. Can you hear me? Is it too loud now? So first of all, I want to thank the organizers, Rogerio, Sheng, Enrico, I don't know, Enrico, where he is, and Geraldine for asking me to step in for Yossi Nir from Weizmann Institute in Rehovot in Israel, for the reasons that were just mentioned by Sheng. Step in is not the same as replace or substitute. It is not possible to substitute a lecturer and a physicist like Yossi, but I'll do my best. And so let's get on with it. I'll try with the fat one and then see what happens. So the plan for the lectures. So the lectures are supposed to be the standard model, physics beyond the standard model, and then I was asked something like conditions for baryogenesis. Okay, so that was the charge I got from the organizers, and so the plan is going to be something like this. Lecture 1, the standard model. Mostly here is probably things you know. I'll try to emphasize things that it may be very useful when we go beyond the standard model. Some technical things, so I am going to be a little bit more technical. Then in lecture 2, I hope that this is going to be beyond the standard model 1, which I'm going to split in Y, going beyond the standard model. And the first part of the standard model, which is supersymmetric theories of physics beyond the standard model. Then in lecture 3, I'm going to talk about composite Higgs models. And in lecture 4, more composite Higgs models. Mostly I'll talk about twin Higgs, which is also a composite Higgs model of a special kind. And of course, the so-called conditions for baryogenesis, which is a simple introduction to some of the well-known Sakharov conditions, but also to what extent the standard model or some of these extensions can actually supply these conditions. Some of these, let's see how it goes today's lecture. Also, lecture 1, 2, and 3, and 4 doesn't mean day 1, day 2, day 3, and day 4. Those who know me know that, I may go really long in some of them, and eventually we'll get to the end, hopefully at the end of the 4th day, but I'm not sure how the division will happen, okay? All right, so how many of you have taken a couple of semesters of quantum field theory? Raise your hand. All right, okay, so everybody's supposed to have taken it, okay, including my own students, good. All right, that's good. So this then should be relatively straightforward for most of you, but I'd like to go through in some detail. So I'm going to consider the whole standard model. It's a gauge theory. It is described by the invariance under a group, which you know is U3 color, SU2 left times U1 hypercharge. This is the gauge group under which we will consider the Lagrangian of the standard model is invariant. And this this is a condition that will never be violated in these lectures. It cannot be violated explicitly. That the Lagrangian is invariant under these transformations. This is a fact that we are based on experimentally, and I'm not going to say much about QCD. It's a theory of the strong interactions at high energies. I will say something about what I mean by high energies in this case. The strong interactions at low energies, we'll talk about this also at length eventually, sometimes on Wednesday. When we talk about composite Higgs models, we start with the strong interactions. But at the moment, I'm going to leave the strong interactions alone. And the reason is that the strong interactions at the time in which we have to actually spontaneously break the weak interactions, the electroweak interactions. These are the electroweak, which I'm going to model like this. These are the electroweak interactions. They are unified in this product group, which doesn't look greatly unified, but that's what we got, okay? And so this breaking of this has to happen because we know that nature is described by a massless gauge boson that comes out of this breaking, which is the photon, and then 3 massive gauge bosons that come out of this breaking, which are the W and the Z. So And in that process, the gluon fields, the 8 gluon fields that come from this from QCD at high energies, they just don't do anything. They don't feel anything. So I'm gonna just avoid talking about the gluons as long as I'm talking about the electroweak sector. for a while, and then we'll talk about QCD and the breaking of some symmetries associated with QCD at lower energies even. And so today, we're going to be concerned with, so this is energy. So here, this is nothing really. This is energy, and that's it. So the electroweak typical energy, which I'm going to call V electroweak, which is about, let's call it 250 GeV. I'll say this in a minute why, is the scale at which W's and Z's acquire mass. Something happened, we'll see what. And there is another scale, which I'm going to call lambda QCD, or if you want, some hadronic scale, right, which is smaller than 1 GeV, and that's where we had to worry about what happens to strong interactions at low energies. But for the moment, I'm going to talk about this, and throughout this whole story of the electroweak symmetry breaking, QCD is just a spectator, okay? It won't do anything, okay? Right. So I'm going to talk about the electroweak sector, the electroweak standard model. And so in the electroweak standard model, what we know, again, is, first of all, is that experimentally, we know that there are charge weak interactions, and that they are described by Fermi's effective theory in the 30s, right, early 30s. And so these charge gauge interactions, maybe I should put the 4, the Fermi Lagrangian is a -4 here. It's a 4 Fermi interaction. This one, for example, is responsible for muon decay. Into a charge electron-neutrino pair. So this muon decay somehow happens spontaneously, and it decays. The way it is at least described by the Fermi interaction, it decays in this way. Here we have the neutrino of the muon, the electron, and the anti-neutrino of the electron. So this is muon decay. Similar decays happen in beta decay for decays of, for example, the neutron. Similar decays happen to pions, et cetera, et cetera. And so what happens is that it turns out that these kinds of Lagrangians, these Fermi Lagrangians with this coupling called G Fermi, describe all of these phenomena. Now, early on, people thought, well, we don't know these kinds of interactions where you have 4 fermions. This constant here has to have units of inverse energy square, right? This is so-called non-normalizable, and I'm going to go into the details. But what if what's doing this is some gauge theory, and it was postulated that there was some intermediate vector boson that had to be charged, okay, in order to mediate this interaction between this muon lepton type current, which is charged, and this electron type current, which is charged. And so this is, so we postulate this interaction right here, and essentially what happens is that if I do this, then I predict that at remember, I don't know what the mass of this object is, but if I measure this constant experimentally from the decayed lifetime of the muon, which I can compute from this Lagrangian right here. I measure this constant experimentally, and then you conclude that that means that the coupling constant, which is here I'm going to call G, and this is going to be some massive object W, G squared divided by 8 times MW squared, should be giving you that experimental number. And so that means that this has to be a massive object. For this to be a point-like interaction, there must be an object that is so massive in the decay that its propagation is extremely suppressed, and that you can then approximate it at the energies that a muon exchange, a muon decay will liberate, right? So this muon, it's 100 MeV. This will imply a very heavy object, and this object has to be in the, assuming this constant is 1, about hundreds of GeV, a couple of hundred GeV. Turns out to be 80 GeV, but that's approximate because G is not 1. So that's the first idea. Of course, if you have, this could be a muon plus and then a W plus, changing this and changing that. And so you have two gauge bosons that are needed to describe nature that have to be massive, right? So you go ahead for a while until in 1972, people realized that they need to have also a neutral current. The discovery of the neutral current neutral currents implied that the existence of a similar object mediating nuclear exchange between neutrinos and nucleons going to neutrinos and nucleons with the recall without any electron coming out, or without or the opposite. And so this kind of discovery implied that now there has to be a third massive gauge boson. So in total, we need 4 gauge bosons, right, in the electroweak theory to explain all the data. QED has to come out of that with a massless gauge boson, which is the photon, and then I need 3. And so this is why the story goes, this is told to me by Glashow, so I suppose it's true, that when he was a student, he walked into Schwinger's office. My student knows the story, sorry about this. And he asked Professor Schwinger, what do I do for my PhD thesis? And Schwinger said, well, I try unifying the interactions, the weak interactions with SU2. Why don't you try with SU2 cross SU1? This is before the discovery of the neutral currents. It's like, for a PhD exercise, it's fine. So that's Glashow's model. That's the standard model. It's an interesting paper for you to read because Glashow didn't know what to do with the fact that these objects were massive. That was violating gauge invariance in the understanding of 1961, right? So he called this generalized invariance. And what he said is generalized means I don't know what's going on, so it's not invariance. I put a word in front, and that's it. So that's Glashow's model. He had one more. Now, there was another model that was unfortunately written in 1972, but in the early months of 1972, which also Glashow wrote with Georgia, saying we don't need 4 gauge bosons. We need 2 charged ones, and we need the photon. And that Glashow-Georgia model is a famous model that lasted for about 3 or 4 months until the neutral currents were discovered. And then Glashow said, well, but I have a model that explains that too from my PhD thesis. So the point of this, what I'm trying to say is that we understand the electroweak sector experimentally. And if you think I'm going to tell you how to make sense of it, why is it like this, the answer is we don't know. Already I'm telling you. Okay? So the point of it is the experiment builds the standard model, and we make sense of it to make predictions with quantum field theory, because we know it's supposed to be a gauge theory, but it is a gauge theory And so, and it has to be a gauge theory of all matter. So the electroweak group, G electroweak, has to be SU2 cross U1. But the problem is that the charge interactions, as you see here, you didn't, but OK. The charge interactions experimentally only talk to left-handed particles. Why is that? Again, don't look at me. I don't know. It's called maximal parity violation. It's a feature of the standard model. It's weird. We have to deal with it, OK? And it's a feature that is experimentally understood because if you look at the, for example, the electron angular distribution coming out of the muon decay, or whatever angular distribution coming out of this free-body decay, and you fit it for only left-handed electrons, in this case, it fits perfectly, 100% with very, very small errors by now. So we know it's only left-handed fermions, participants in this. So we're going to call this one SU2 left. Now this U1, you say, well, is that just the electromagnetism, the U1 that, the photon, electromagnetism? And the answer is going to be no. The reason it turns out, is multiple, but we know the electromagnetism respects parity, okay? And somehow, if it turns out that the charge interactions do not respect parity, then I have to have a U1 here that respects parity, which is, yeah. However, these interactions that were discovered here do not respect parity, do not violate parity in the same way that the charge interactions do, but they do violate parity. So this one cannot be electromagnetism because somehow it also has to violate parity. And so I'm going to give it a name, hypercharge, not charge, hypercharge U1, and that's the standard model gauge theory. Tudo bem, Enrico? Enrico? Long time no see. Yes. Anyway, so essentially, we know the gauge group experimentally, and now I'm going to say how is it that everyone is going to transform under these gauge interactions, okay? Now, so the first thing is it's a chiral gauge theory, which is very dangerous. But it's very important for reasons that we'll see later. It's a chiral gauge theory, very important for this school, I mean. It's a chiral gauge theory, meaning that the couplings of the left-handed chiralities are different to the gauge bosons than the right-handed ones. And that is potentially dangerous, as we'll see later on. Now, how is it that matter, the left-handed fermions, transform? What does it mean that this is the gauge interaction? It means that, for example, if I have my covariant derivative applied to a left-handed fermion, okay, so what I expect to see in the covariant derivative are the interactions of the gauge bosons of these fermions, right? So I expect to see, obviously, the good old derivative, okay? But then I have to introduce a coupling. I'm going to introduce it in here. I don't have to, but it's useful. G, which is going to be the coupling of the SU2 part, okay? And this coupling G, and then I'm going to introduce 3 gauge bosons, A, mu, 1, 2, 3, associated with the 3 generators of SU2. SU2 has 3 generators. You all raise your hands, so you should know that. And then the generators of SU2, which are the Pauli matrices divided by 2, but I don't like to write that all the time. So these are the Pauli matrices divided by 2. And then I'm going to have to write the generator, the coupling of the U1, which I'm going to call G prime. I'm going to have to stick some name for this gauge boson, which is not the photon. I'm sorry about this. This is not the photon. If you've ever seen the photon with an A and B, this is 1, 2, 3. And then finally, this has to have a charge, which I'm going to call the hypercharge. And this is the hypercharge of this particular left-handed lepton, whatever it was, okay? applied to the left-handed lepton. So this is the covariant derivative of the left-handed lepton. On the other hand, under this group. And on the other hand, the covariant derivative of a right-handed fermion, of a right-handed fermion is simply this. Then I just skip here, G prime, the gauge boson of hypercharge, and then I have the hypercharge of the right-handed fermion, whatever that is, times the right-handed fermion. So there's one term less, right? That's it. Very good. What this means is that when I transform the left-handed fermion field under the gauge group, this is what happens. E to the I alpha A x T A times e to the I, let's call it beta of x. And here I'm going to have to squeeze in the hypercharge of the left-handed field times the left-handed field. So there are two exponential factors. One is the parameters, the local parameters of the gauge theory, alpha 1, 2, 3, which is completely arbitrary, for the SU2 left. And also there is this one, which is a different parameter for the U1 hypercharge, whereas for the right-handed, obviously, I only have the second factor. The right-handed field transforms like this, beta of x, the hypercharge of the right-handed field, times the right-handed field. Okay, so that's what it means. So I know the interactions, which are the gauge interactions. And now the question is, what are the representations of these matter fields? So we're going to have the gauge bosons of this electroweak theory. Remember that the gluons are spectators of the whole thing. But here I can have quarks, I can have leptons, okay? Any quarks and leptons. And then the question is, what are the representations of this object? You get to walk a bit here. It's good. All right. So how am I doing? All right. This is good. This is good. I hope you had a good snack. It's too big or too small? Oh boy, this is not easy. All right, so first of all, let me look at my notes. Okay, so the representation, what happens here is that this is a very simple thing. It's very simple in this case that we have, for the left-handed, fermions, how is it that the left-handed fermions are going to be represented? Well, if you look at this, the covariant derivative contains these SU2 matrices for the left-handed fermions, and implicitly you should ask, if this is a 2x2 matrix, right, then there's got to be some matrix here, which of course it is. It's the identity in 2x2. The identity, well, imagine that I wrote the identity in 2x2, okay? And of course here, it's also the identity in 2x2. What this means is that, of course, here, the derivative is a diagonal operator in SU2, that's obvious, but also the hypercharge generator as the charge in the case of the U1, is a diagonal generator when you embed it in the SU2 language. But that means that there must be some SU2 index for a left-handed fermion. And so what we call a left-handed fermion has an internal index, which has to do with the fact that it actually transforms under SU2. So it is a non-trivial object, right? So let me put it this way. The mu has indices, which are these matrix 2x2 indices, right? I and j. And so if you apply this to the left-handed fermion, then there must be some sort of index here that is coupled with one of these two indices. Now, this is in the simplest form of representing the fermions that I'm going to use here, which is actually the standard model representation. It turns out that I'm going to use the leptons as doublets of SU2 left. The leptons, not the fermions, I'm sorry. Is that I see this letter and it says leptons, I don't know. So the fermions that are left-handed are doublets of SU2 left, okay? And so that means that when I talk about the quark doublet, I'm going to put it like this. This is a left-handed doublet, right? This left-handed doublet of quarks has to have two fermions, two, in principle, four-component Dirac fermions. One, I'm going to write it as a column vector like this, right? So this is the definition. This one I'm going to call U left, and this one I'm going to call D left, okay? And the same thing with the lepton left-handed doublet. There's going to be a neutrino. Let's say I do the first family, the neutrino, and then the electron. They're both left-handed, okay? So when I talk about the left-handed fermion in the standard model gauge interactions, I always talk about this is the object that interacts, but it contains an internal index, J, where Ij are there are 2x2 matrices, and so these indices have to be 1 and 2. Okay. On the other hand, if I'm talking about the right-handed lepton, the right-handed fermions, the right-handed fermions are singlets of SU2 left. In other words, they don't transform under SU2 left. When I do a gauge transformation, they don't feel this interaction. Like neutral particles are singlets of the U1 electromagnetism, for example, right? They're not charged under that interaction, and so these objects will be just by themselves. And and so, for example, we're going to have a right-handed electron. We're going to have a right-handed up-type quark, down-type quark. In principle, I'm going to put this object here, the right-handed neutrino, because at the moment I have no reason why not to put it there. But in a minute you'll see that it's like not really there, at least in the standard model. But so let's put it like this. Okay, good. Now, we're going to have to derive somehow this. We know everything about how the SU2 left interacts. There's nothing, of course, I don't know the coupling. I have to measure the coupling from experiment. But there is nothing here I don't know about SU2. It's just, these are the generators of SU2. Pauling matrix is divided by 2. On the other hand, here, I have to assign charges, hyperchargers, both to the left-handed and right-handed fermions when they interact with the hypercharged gauge boson. That I have to assign somehow, okay? And we'll do that in a minute. All right. Now, one thing we can already see is that there is a bit of a problem with this gauge interaction before I even compute anything. I said that the Lagrangian of the standard model must be invariant under these gauge transformations, all of them, but in particular also this, right? And it turns out that there's a problem with this at this point, okay? So let me talk about this. And please do interrupt me anytime for questions or comments or anything, okay? Okay. All right, so now, okay, so you saw this. That's a problem. And the reason why it's a problem is that is fermion masses. So the fermion masses, what's a fermion mass? A fermion mass term, this is generically, is written like this. Again, let's say it's a Dirac fermion, and so this is the mass of the Dirac fermion, of course. Okay, but of course this is equal to m times psi bar L psi right plus the Hermitian conjugate. Okay. And you see that's a bit of a problem because the gauge transformation for these two fermions, it's different, as we can see on the other board. And so this is not gauge invariant, okay? So not gauge invariant, as you can see. I don't know if I need to do this, but it goes like, you know, whatever m is, and then you have psi bar L e to the minus I alpha A of x times dA. And then I have e to the minus I beta A of x. And here I have y of the left-handed fermion, right? And here I'm going to have I beta of x, the same parameter, the same parameter of the U1 transformation, but with a different hypercharge. This is different than this one. So not even this piece is actually canceling, okay? So this term, obviously plus the Hermitian conjugate, is not gauge invariant at all. This term is hanging out there waiting for a plus I alpha here that will never come, okay, because this is right-handed. And then, of course, these two not even cancel. Okay, so fermion masses are forbidden by the standard model gauge transformations. It gets worse. First of all, we know fermions have masses. We measure the mass of the fermion, so that's a problem, right? It's not a problem for us, it's for the standard model. Okay. All right, the other thing that is pretty obvious is that I didn't write down the gauge boson part of the standard model. The gauge boson part of the Lagrangian so the gauge boson Lagrangian, as you will know, we have this SU2 L is FA mu nu, A mu nu. So these are, this is the kinetic term for the SU2 left gauge bosons, okay, where this is non-abelian, and so, you know, you have to know all these things. And then we have the B mu nu. B mu nu is the kinetic term for for the transformations. I'm sorry, for the U1 hypercharge. And then, of course, A mu mu, let's say A mu, let me just call it A mu of X as the contraction of the gauge bosons with the generator. So this is one big happy matrix of gauge bosons, right? This is a 2x2 matrix of gauge bosons, which I'm going to call A mu, maybe like this. And so A mu, as a matrix, it transforms as some gauge transformation G of X times A mu times G dagger of X minus I over G d mu of G of X times G of X. I didn't count on this part. All right? Where this G of X is, of course, G of X is the SU2 transformation. It's defined to be e to the I alpha of xta e to the I. I'm sorry, this is just the SU2 part, right? So this is the SU2 transformation, and this is the SU2 transformation for the gauge bosons, okay? And of course, B mu is just B mu nu. B mu transforms in the usual way, say U1, B mu of X minus, or I'd say 1 plus G prime d mu of what I call beta of X. Okay? Now, these gauge transformations are respected by these two terms, but there is no other thing I can write down, and in particular, I cannot write down mass terms for the gauge bosons. So the mass terms are forbidden by gauge invariance, and I don't like to call them generalized gauge invariance, despite Glashow's name. And so that's a problem. How do we explain that the gauge boson masses, all the masses are forbidden in the standard model? So these terms are forbidden also. So we conclude that the standard model gauge theory that we built experimentally tells us that none of the particles can have masses as it is in this theory, right? None of the particles, of course, we know many of them have masses, most of them, okay? And so that's the problem. Now, this problem, okay, there is an interesting story, but I don't have a lot of time for this. I have 45 minutes? Didn't I study? Yes, I have 45 minutes. Yeah. Okay, but in any case, this is a problem. And so, and I'm going to specify in the electroweak standard model, because there are masses in the strong part, in the other part, which I'll talk about a couple of days, which are not related to this mechanism. There are, I don't know, masses of hadrons and things like that. Okay? Yes. The gauge bosons are real fields.
But you can consider a Proca mass term.
Yes.
So this kind of problem will be avoided. Don't you think about?
Why?
Because in the Proca mass, the mass term is, for example, A dagger, not AA, because it's charged particle, for example. So you can avoid this kind of problem, not in the fermion. I'm saying about only the massive terms of the gauge bosons.
You mean in the charge part of the gauge bosons? I mean, first of all of the gauge bosons are real representations, adjoint representations of SU2, and of course U1 is a real representation. So there's no dagger, right? It's a real representation. The adjoint representation, which is the representation always of all the gauge bosons, are real. Now, Proca Lagrangian, I can always write it. That doesn't mean that it's gauge invariant. It does not mean, the Proca Lagrangian, I can always write it down, and there's no problem having the equations of motion are essentially a bunch of Klein-Gordon equations for mass, for each component. It's not a problem. The problem is when I impose gauge invariant. The Proca Lagrangian will not be gauge invariant. On top of the fact that even if I write down the charge ones directly, so the way we're going to write the charge one, remember that they are not in the fundamental representation of the group. So I cannot put them in a doublet of SU2. They have to be in a triplet, right? The charge ones have to be in a triplet, like the pions. Think of the pions. The pions, they are pi plus and pi minus, but they're not a doublet of SU2. They are pi plus, pi minus, pi zero. I cannot avoid them. And so here, there are the three of them belong to a real representation, which because the triplet representation is a real representation of the group. So I don't have the dagger. Despite the fact that the pions are two of them are charged, right? They belong to a real representation of SU2. Pi 1, pi 2, and pi 3 are real scalar fields, let's say. Yeah. Any more questions? This is a good time for questions, I guess. All right. Now, the origin of mass in the electroweak standard model is related to a phenomenon called spontaneous symmetry breaking. Now, spontaneous symmetry breaking, I'm not sure about spontaneous, what does it mean in here, but there's no symmetry breaking. So it's a terrible name, like many names, but so the rest of this time will be for me trying to get out of your head that the symmetry is being broken at the same time that we actually have the masses. Because I said the symmetry forbids the masses. I'm not going to break the symmetry at any point, yet we're going to get masses. Okay, good. Now, let's see. First of all, what is spontaneous symmetry breaking? Spontaneous symmetry breaking enters in a number of physical systems, not just in this electroweak standard model. And so we can actually give a quick quantum mechanical presentation of what it is, so to then apply it to our case, okay? So spontaneous symmetry breaking means that the symmetries of the Lagrangian, which will not be broken, I told you the Lagrangian will remain invariant under the gauge symmetry, are not the same as the symmetries of the ground state. That's all it means, okay? And so a very generic way of understanding this if I can find the pages, is the following. Now, we know from Nether's theorem that for each continuous symmetry, of the Lagrangian, we have a conserved current. That's what we know. If there is a continuous symmetry, we have a conserved current, which means that we have a conserved charge. Which is defined as the volume integral of the zero component of the current. That's the charge. And the charge is conserved too, if the current is conserved, because the time derivative of the charge is equal to the, here we have the time derivative of the zero component of the current, right? This is the time derivative of, now it's partial because this is a total derivative, but I go into integral, and this is the partial derivative, okay? But from here, I know that I can write this as the divergent of the spatial part of the current. This is just this equation written in components, right? So this equation is D0, J0 minus the divergent of the current equal to 0, right? This is the same equation, so I can replace this term by this term. This term, however, there is a theorem, which I always mixed up the name, but that's okay. I don't even say which one is in my notes, but okay. That tells you that the volume integral of the divergence of a vector is going to be a surface integral of the surface element vector, the current for a surface anyway, in particular at infinity, and this is equal to 0. Okay, and so essentially what this is saying, look, I mean, if you have charge coming out of a volume, okay, the amount of charge that comes out per unit time has to be compensated by the divergence of the current, which is essentially what's going through the surface of this spherical volume or whatever volume, okay? Very good. So the charge is conserved, okay? So this is the same as that, right? Very good. Now, suppose that I have in Hilbert space these states, some states that transform under this symmetry. Okay, so now I have these states. Under this symmetry, I consider this state, I don't know, I'm going to give it this name, okay, that it will transform into e to the I, some arbitrary constant alpha times the charge times the state. This is the action of the symmetry of a charge Q on the state of the Hilbert space where alpha is a constant. Okay, very good. And what about the vacuum or the ground state? Now, in general, this state is different from the original one, right? But I want to know if the ground state is invariant under the symmetry or not, okay? So under the symmetry, the ground state goes to e to the I alpha q ground state. Is this equal or not to the ground state? Okay? Well, if it is equal, that means that the charge, if it is equal, that means that the charge applied to the vacuum is equal to what? Not you. Okay, anybody. It's equal to 0, right? I mean, because all of the powers, the only power in the exponent that can work is the 1. All of the other ones are powers of the charge acting on the vacuum. They all have to give me 0, okay? So this is when a charge annihilates the vacuum, it means that the vacuum or the ground state is invariant. This is something we're going to work on a lot, okay? And now if e to the I alpha q applied to the ground state is different from the ground state, obviously the charge applied to the ground state does not annihilate the vacuum, okay? These are the two situations here, okay? Yeah, okay? I'm going through these babies like, yeah, I have to maybe write smaller. Okay, so now, really going slow. Yes?
So Q commutes with itself, so wouldn't automatically commute with the exponential of alpha Q, and therefore would already be 0 or not 0. Depending.
I'm sorry, what?
Q commutes with itself, right?
Yes.
So it commutes with the exponential. So if it is 0 or not, it only depends on whether you start with the Q vacuum equals 0 or not, right?
Right. It depends on whether either of these two happen. Yeah, exactly. So if it annihilates the vacuum, then this happens. And if it doesn't, then it's just like any other state which changed. So the vacuum is not invariant, right?
Yeah, I don't know if I followed, because if you start with Q acting on vacuum before the transformation equals 0, right? And then you do the transformation and apply again, you can always change the exponential by Q, and then it would be 0 again, right?
Well, no, wait. Either Q annihilates the vacuum or it doesn't. So no matter how many times I'm going to apply Q with the exponential or without, it's not going to annihilate the vacuum if this is the case, right? So
yeah.
Even if I start, you were saying to do this? Is that what you're saying?
Yeah, exactly.
Okay, so this, right? If Q does not annihilate the vacuum, is that the example you're giving, right? If it does not annihilate the vacuum, then this is going to be something different from the vacuum. No matter how many times I apply Q. I apply this, and then I apply it again through the 1, and it's still going to be different than the vacuum.
Yes. Yeah, my point is that...
It's one more power of Q in the exponent.
Yeah, exactly.
So it doesn't change anything.
Yeah, my question was that it doesn't matter whether you apply or not the transformation. The fact that it will annihilate or not, it's...
Well, but this is the form of the transformation. This is how I know a state in Hilbert space is or not invariant under this transformation. I have to apply the transformation in this particular way. This is the way symmetry acts on the Hilbert space states, right?
Okay.
Not Q, but this, right?
Sure.
All right. It has to be unitary transformation on the Hilbert space states, right? That's why I'm using the exponent. But of course, you're correct. Once I expand, all that matters is whether this happens or this happens. All right? Okay. All right. So let me just make the point. Maybe this will so the question is, what happens when the vacuum is not invariant? So let's assume this case, right? When the vacuum is not invariant under this transformation, that means that e to the I q, alpha q applied to the ground state is some other state that is not the vacuum, and I'm going to parameterize it by this arbitrary parameter alpha, right? So this is not the vacuum, okay? Now, notice that I never said anything about the charge conservation. All I'm saying is that the charge is not annihilating the vacuum, right? And it's taking me to another state that is not the vacuum that I'm calling alpha, okay? So we still have the situation where the derivative of the charge is 0, okay? And so this situation, when this is the case, and then the derivative of the charge is still 0, it's what we called spontaneous symmetry breaking. This is the situation, okay? The situation where the charge annihilates the vacuum and the derivative of the charge is still conserved is the normal realization of a symmetry. It's supposed to be 6 realization. Okay? And this is the situation we are interested in. Okay? Now, there is an important consequence to the spontaneous symmetry breakdown. And this is actually a theorem, but it's easy to see in this particular case. But and so let me just show you this, and then we go to an example and finish or something. Let's suppose for a second that I have the Hamiltonian applied to one of these states alpha, okay? Now, what do I do about this? What do I know about this Hamiltonian and the charge, our friend the charge? What is this? I mean, up here. What is this? It's the same, but it's in this situation. What is this telling me about Q and the Hamiltonian? The commute. Okay, very good. So I know that this is equal to the Hamiltonian times e to the I alpha Q times the ground state, which is the definition of the state alpha. But H and Q obviously commute, so this is e to the I alpha Q, you know, this the commute, and here is the Hamiltonian applied to the vacuum. Now, the Hamiltonian applied to the vacuum gives me the ground state energy times the vacuum. So this is equal to the ground state energy, which is a number, times e to the I alpha Q times the vacuum, which is the same as saying the ground state energy times the state alpha. So the Hamiltonian applied to the state alpha tells me that the state alpha, all of these states alpha, arbitrary many of them continuously defined because this is a continuous parameter alpha, they are eigenstates of the Hamiltonian with the same energy as the vacuum. They are not the vacuum. They are not the vacuum because I said that the charge does not annihilate the vacuum. So alpha is not the vacuum. But they are continuously degenerate with the vacuum. So how come? Well, this is Goldstone's theorem. is a version of Goldstone's theorem. And Goldstone's theorem, which was proposed by Goldstone and never proved by Goldstone by himself, proved by Goldstone with Weinberg and Salam 3 years later, so he got some help, okay? But it's called Goldstone's theorem, okay? Has many realizations, but this is the most basic, simple way of seeing it. If you have a charge that is conserved, but it does not annihilate the vacuum, this is spontaneous symmetry breaking. That's what we call it. The Lagrangian is still, the charge is conserved, the Lagrangian is invariant under the gauge transformations, for example, or some global transformation. But there must be a continuously the set of state degenerate with the ground state, right, that I can access without any energy cost from the ground state. And those are called massless excitations in this case. So alphas are the alpha is a state of gapless excitations. Gapless means that I don't need any energy from the ground state to get to them because they have the same energy, but they are not the vacuum. Okay. And in the context we're going to use these are the so-called Goldstone bosons, okay, and they're going to be very important for the spontaneous symmetry breaking of the electroweak theory. And so I have what 10 minutes, 5 minutes, 25. Oh, what a relief. All right. So, of course, we're not going to finish the standard model today. Don't worry about it. This is going to be, but we're going to do a lot of it. Don't worry, don't worry. This is going to squeeze a little bit. I have to do these things with care because of what comes next. So, anyway, so let's consider a system with a global U1 symmetry. A global U1 symmetry is, for example, the Lagrangian for a complex scalar field, okay? So a complex scalar field, I'm going to write it a little different. I'm going to put it 1/2 here, but it doesn't really matter. D mu phi star, D mu phi, there's going to be a mass term 1/2 of mu square phi star phi plus, minus at the moment, lambda over 4, why not? Phi star phi. So this Lagrangian is invariant under phi of x goes to e to the I alpha phi of x, where alpha is a real constant. Now, that's the Lagrangian, and that's the invariance, and everybody should be cool with it, right? It's invariant under this alpha real constant. This is a continuous symmetry. There is a current. You know how to do it. But I'm worried about the ground state. Is the ground state what is the ground state? And so the potential is what's going to determine the ground state. So let's write the potential, which is 1/2 of mu square phi. Okay, and this, of course, you've probably seen a lot. Sorry, it's a square here, it's a quartic term. Now this potential, if so, what is the minimum of this potential, right? If I take the derivative of the potential with respect to phi star phi, right, and equate to 0, then the minimum of the potential is when phi star phi, let's call this at the minimum, okay, you know, I chose this, so there's a 2 here in the derivative, so it's a 2 with a 2. And so the minimum will happen when for minus mu square divided by lambda. Okay? Now this is a little bit funny because, well, if mu square is the mass of this field, it's mu square is positive. I mean, the mass square, so mu square is positive. This is clearly has to be a positive quantity or 0, right? I mean, this is, you know, the absolute value of phi square, right? So this this can be like this, positive or 0. So when mu square is positive, then this has to be 0. When mu square is negative, on the other hand, then this is not 0. This is going to be minus mu square divided by, well, this is now a positive quantity, okay? Divided by the coupling. And I'm going to call this v square. Some number v square. V square. Positive, right? Now, of course, you say, well, if the mass of the particle square has to be positive. Well, what if it's not? Okay? Okay. Condensed matter physicists in the audience? 0. Okay, good. So that's okay. I'm going to give 2 examples of spontaneous symmetry breaking that may actually have something to do with understanding this thing of the mass square being negative. But then for us, this simply is a parameter, right? It means if mu square is negative, that means that the description of this theory with this field is not a stable description. I have to have, this will be the mass square of this scalar, complex scalar field, okay? Assuming that I have, so here is the potential as a function of phi star phi first, then we'll do it as a function of phi, but so the potential, if it turns out that that there is a minimum of the potential for mu square positive, that minimum is going to be 0, okay? But if it's not 0, it's going to be some other value, which I called here v square, okay? V square, right? Now, what happens is that the description of this theory with this scalar field, where this was the mass, but the mass square was negative, is clearly the description of expanding the theory around this minimum. But this minimum is not stable. It has to eventually go to this minimum. And so this will be the actual true minimum of the theory about which I should expand my quanta. So I have to rewrite, do a change of variables of my theory to expand my, let's call them harmonic oscillators around the minimum, the global minimum, so that I have quanta that start from 0 here. Here, that's just not the case, okay? So having mu square negative is just telling you that the system is going to undergo a transition to the true vacuum. We're going to go through this a lot, okay? Now let's think, for example, of this situation up here. Let's think of, for example, of a system that's easy to visualize, a ferromagnet, okay? A ferromagnet is a bunch of spins that interact with some interaction that tends to align them, okay? In other words, you minimize the interaction. Remember that the energy was minus some okay, I don't want to use mu, but it's some dipole, which I use mu for the dipole when I do electromagnetism, but some dipole thing, and then times the spin. And so essentially, I'm sorry, spin 1, spin 2 times the dipole strength of the interaction with the minus sign. And so this will be minimized when they are, of course, aligned. On the other hand, if you have temperature, it turns out that the spins are randomly pointing everywhere. And so temperature, at high temperatures enough, if this interaction is not strong enough, then, happy randomness wins, right? Well, this is expressed in this way. The free energy of the system is actually the energy of the interaction minus temperature times entropy. And so you can minimize the free energy at high temperatures. It's going to be better to maximize the entropy, to minimize. This guy, it's going to minimize the free energy. So at high temperature, randomness wins. Whereas at low temperatures, maybe the strength of the alignment will win. So if you go down in temperature, this is going to win at some critical temperature, and all of a sudden, all of the spins are going to start aligning in one direction. Now, how come? Then you're going to observe a macroscopic magnetization of this material at low temperatures, and this magnetization has to point in some direction. In which direction is it pointing? I don't know. Let me just heat it up again. Oh, now it's pointing in a different direction when I cool it. It just picks a direction. It has to pick a direction that, and somehow it's random, okay? That's spontaneous symmetry breaking. The Hamiltonian of the ferromagnet is O3 invariant. It's invariant under rotations, okay? Whereas the ground state magnetization has to point in some direction. So there is a field called magnetization that acquire some value that's non-zero, right? And it points in the direction that is randomly chosen. That's spontaneous symmetry breaking. I didn't break O3 invariance explicitly in the Hamiltonian. There was a process in which something just changed signs, and all of a sudden, everything started aligning, okay? Another example is a superconductor. In a superconductor, you'll have essentially this theory, more or less, okay? Actually, it is exactly this theory. It's a complex scalar field, and this term here, mu square, is actually some coefficient, I don't know, some coefficient times temperature minus temperature critical, okay? So at high temperatures, mu square, the coefficient of the quadratic term is positive. Below the critical temperature will be negative, okay? The point is that this is a description of spontaneous symmetry breaking in various different cases. Now, in the relativistic theory, it sounds a little weird for me to start with a mass square that is negative, but you have to just understand that all I care about is if the ground state is respecting or not the symmetries. So now I have to go, first, before I have to go and change variables in order to go to the correct variables that will give me the correct description, right? Now, the way to do this is to imagine that I have, phi, this phi of x is, I don't know, phi 1 of x plus I phi 2 of x, where phi 1 and phi 2 are real scalar fields, right? Okay? And then it turns out that this is phi star phi, but I have to plot the potential in phi. So how do I plot the potential in phi? Well, God help us, because I don't know how to do these three-dimensional things. But if I do it in 2 dimensions, right? Here is phi 1 and phi 2, the imaginary part. phi 1, phi 2. What I know about phi 1 and phi 2 is that phi star phi at the minimum, which is equal to phi 1 square plus phi 2 square at the minimum, no? At the minimum of the potential, this should be equal to v square, okay? And so there's got to be a circle in the, this is a circle, okay, of radius v, okay? A circle in radius v, and so if you imagine the potential is coming out of the plane vertically, right? And so here is what I'm trying to do. So here is phi 2, here is phi 1. Imaginary and real part, here is the potential. And there is a minimum of the potential here. I wish I had gotten this 3D version of the there was a printer and in Trieste. They wanted to show to me a 3D printer in ICTP in Trieste, and they said, "What do you want us to print?" And I said, "Just print me the potential of this theory." And they said, "We'll mail it to you." I'm waiting, but in any case, so here is the minimum of the potential, right? And here would be this phi square equal to 0, but now the minimum of the potential is here in this place. I displace this, so I get the 0 here, but it's irrelevant, so I can get this thing. So the minimum here, right? And so somehow this is the minimum of the potential, or if you want, here, right? This is V, okay? But the question is, where is the vacuum? Where is the ground state in this circle? I have to decide that any point in the circle will satisfy this condition, which is the only thing I know. So I have to pick a point arbitrarily. I can pick this point. I can pick this point. So this would be that the expectation value of the field phi is equal to V, is this point. Or that the expectation value is equal to I times V will be this point. Because you get I or minus I, it doesn't matter because you get, square. And so the question is, the picking of one point is the breaking of the symmetry spontaneously. Now, as you can see, there are all these continuous places at the bottom of the Mexican hat. Look, where is Lorenzo? You didn't bring a hat. See, it would have been it would be so helpful if I knew you were coming. Anyway, so at the bottom of the wine bottle or Mexican hat, whatever you prefer, you know that there are all these points with the same energy. Well, those points are our alpha states over there. I don't need any energy to get to the other points. I just need to pick a point and call that one my ground state. But then I can access all of these other points with any energy gap. This is the direction of the Goldstone boson. So if I do from this point, okay, this is phi 2. Let's just call it phi 1, okay, phi 2. Let me just say that I'm going to choose this point, and then phi 2 has a 0 vacuum expectation value, so that, of course, this is satisfied. Then I'm going to expand the theory around this point, but there are two directions. There is a direction in which I have a cost. This is terrible. Let me go a little bit higher here. There is even worse, okay. There is a direction around which there is a cost of energy if I go perpendicular to the circle. This direction has a cost of energy, whereas this other direction, perpendicular to the circle, in the direction of the circle, is the direction that has no cost, okay? So there's going to be an excitation that is going to be massive in this direction and a massless excitation in this direction. So if you actually do the correct change of variables, you can see exactly that happening. And no matter which variables you choose, you're going to see that happening. And then we're going to use that to death to break the symmetries of the standard model. First gauge, and then the actual symmetry. Okay? So this is the most important mechanism for understanding mass, the origin of mass. But I still have a ways to go. So here, no, this is not what I'm looking at. So if I now choose the following, I'm going to choose that phi of x is parameterized like this: v plus eta of x plus I psi of x. Psi and eta are real scalar fields. Clearly, this is phi 1, and this is phi 2. I just changed their names, but the expectation value of phi 1 is v, means that the expectation value of eta of x in the vacuum, of course, is equal to 0, and also for psi of x. So now, expanding around this point v over there, that I chose to be real, so it's that particular point, the vacuum expectation value of phi 1 equals to v, expanding about this point, now I have my correct fields, real scalar fields, that don't have any quanta, any value in the ground state, which is what I want, okay? And so when I do that, when I replace this in the Lagrangian, this is the exercise. So this is the exercise. Then I get that the Lagrangian is going to be 1/2 d mu eta plus 1/2 d mu psi minus m square eta square plus interactions maybe, but we'll see what happens. But the quadratic terms in the Lagrangian are the kinetic terms for eta and psi, and then there is a mass term for eta and no mass term for psi. There's no psi square. So who is eta? So clearly the mass of eta is equal to the square root of 2 times m, and the mass of psi is equal to 0. Okay? So here, is an Naboo-Goldstone boson. Who is the Naboo-Goldstone boson? Is the massless particle that corresponds to the excitations around the circle that do not cost any energy. Okay? Now, in this other 1 minute, so this is an exercise, okay? In another part of the exercise is to prove, and it's trivial, but it should be, to prove that if I parameterize the field, if I do my change of variables a little differently, to prove that I get exactly the same theory, where there is a massless particle and a particle with a mass equal to square root of m squared. Incidentally, look at the sign of the mass of eta. Is the correct sign. It's not m squared negative. So this is, you need to get a 2 and a 2 to get this result, but the sign is correct, okay? So you have to do this exercise, convince yourself, and finally, if the other part of the exercise is to prove that if instead of parameterizing the field by real and imaginary part, I parameterize it in the following way. Okay, if I say that phi of x is equal to e to the I some field pi of x divided by, I have to put a if a dimensionful constant, because if you remember, pi is if pi is a real scalar field, then it has units, but the argument of an exponential should not have units. So I have to divide by some scale that I'm going to call f, and you're going to tell me what it is. Okay, so this, and then here, I'm going to use v plus sigma of x. You have to prove that if I use this, so use in the Lagrangian of phi star phi, the question 1 is who is f, and the question 2 is the spectrum of the theory, the masses, etc. Okay, and of course, this is for you to convince yourself that it doesn't matter how you parameterize the complex scalar field, you're always going to get this spectrum, a massless particle and a particle with this particular mass, and that's independent on what you're going to do. Okay, and f is going to obviously be related to v, but I'm not going to tell you how you fix it. Okay, I guess I have to stop.
Yeah, I think maybe maybe if you have a very, very quick question, otherwise we will move all the questions to the discussion session today. Anyone have a very quick question? Okay, I guess not. Okay.
Just thinking in advance for the standard model, I'm curious, what are the conditions that one has to fulfill in order for, if you have a set of generators and even if they are broken, there is a combination that will remain symmetry, like electromagnetism in the standard model.
So, yeah, so here, what we did here was very simple because it's a U1 global symmetry, so there is only one generator, and either it's broken or it's not. Either the charge annihilates the vacuum or not. In this case, it doesn't. As Lorenzo said, in a bigger symmetry, the generators of the symmetry may or may not. These are the chargers. So there are many chargers instead of one. And some of the chargers will annihilate the vacuum, and some of the chargers will not. So that's really the main focus of how to get the standard model to work. So I hope to do it in the first half tomorrow. So I short of doing it, I basically, but essentially the point of it is that we write the charges as the generators acting on the vacuum, and then we're going to ask that some combination of the generators or some generators do annihilate the vacuum so that the photon remains massless, for example. And we're going to see that it cannot happen with each individual generator, but there is a specific combination of generators that still does that. And so that's supposed to be the electric charge generator. That's the way we're going to do it, yeah. We're going to force the electric charge to do what we want it to do, and then the rest of the theory will be fixed once we do that. Will be a prediction.
Okay, I guess maybe it's lunchtime. I think we'll try to get back by at 2, so that we keep on. Possible. Or should we? Yeah, we'll try to start again at 2, so that we keep. And for lunch, I think today is a holiday, so if you want to go together, I think we will gather at the entrance.